Okay, I'd like to tell you how to calculate the magnetic flux for a non-uniform magnetic field. Okay, so for a non-uniform magnetic field, this is one example. Let's say we wanted to find the flux that was going through this hoop, and that flux would be due to the magnetic field of this wire. Now, the reason I say that's a non-uniform magnetic field is because as you go out, the field gets less and less. So as you might guess, there's a lot of flux in this part of the hoop, but as you go out this way, it's less flux and less flux. In fact, if we move this hoop to infinity, there'd be no flux through it. Okay, so let me show you how you do this. First of all, we're going to need to know what the magnetic field is at any point along the way. So let's just quickly apply Ampere's law. So to apply Ampere's law, say if I wanted to know the field, say at that point right there, we want to know the field right there. Then I'm just going to draw an Amperian loop. Now I'm going to try and draw this in 3 dimensions, but that's my Amperian loop. And let's see, the current is going up like this, so the field wraps around, and so the field is going to look like this. Draw that in black. So the field's going like that, like that, like that, like that, like that. And so are the DLs. And so if I apply Ampere's law, I say mu naught times the I through the Amperian loop, that red loop, that's equal to the closed loop integral of B dot dl. Remember, this is not magnetic flux. This is just the closed loop integral of B dot dl, or the closed path integral of B dot dl. Now, how much current's going through there? All of it. So I'll just say mu naught times I. And you see how B is parallel to dl at every point along the way. Here's a dl, here's a dl, here's a dl, here's a dl. So B is parallel, so I can get rid of the dot product. And so I'm just left with B times dl. And then B is going to be the same at every point on this loop, and because of that, I can pull that B out of the integral because of the symmetry. Why is B any stronger here than here than here? And so I have mu naught I is equal to B times, I'm going to sum up all the DLs. And when I sum up all these DLs, I shouldn't be surprised if this distance is R. I shouldn't be surprised that that's going to give me 2 pi r. So bringing that 2 pi r on the other side. The B for a very long wire, I guess for an infinitely long wire, is mu naught I over 2 pi r. Okay, I will need that for this problem. Okay, now as you might see then, that I'm lucky in the sense that the B is always perpendicular to the DA. See the DA right here? Let's say that's into the page. The DA is points perpendicular to the little area there. We give it a vector nature, and we say it's pointing perpendicular or normal to the page. Point it that way. And so is B. So I can get rid of the dot product with my flux formula. But I can't pull the B out of the integral because the B is different at every part along the way. What I am going to take advantage of is the fact that the B is not any stronger or weaker for these points here. All these points have the same B because they're all the same distance from the wire. And so I am going to put a strip down here, and I'm going to have this strip be really thin. I had to draw it thick so you could see it, but if I call that thickness dr, then if that's really infinitesimally thin, then you see I can make the argument that the B here is the same as here, as here, as there. That the B there is the same as there, because it's infinitesimally thin. And we'll say that this is a distance r away from the wire. By the way, our hoop right here, it's got a width w, a height h, and it's a distance, its left side is a distance a from the wire. And what am I trying to do? I'm trying to find the magnetic flux through this hoop. Okay, well, you see how, do you remember how with this equation, with the magnetic flux equation, if, oh, I don't mean for that. Let me get rid of that. This is the flux equation. It's B dot A. Remember, if the B is in the same direction as dA, I can get rid of the dot product, and if B is uniform, I can pull the B out, and I'm left with just a bunch of dAs. Well, that's true for this. See how this little area here, the shaded region, I'm going to make the argument that B is parallel to dA, and B is uniform. It's just that it's a really, really tiny area. So because of that, because that's a really, really tiny area, that's a really, really tiny flux through there. In fact, I'm going to say that the flux through our shaded area, through this little area, is going to be equal to whatever the B is there, times that little area is what that little area is. Notice I don't have to worry about the dot product anymore, and the B is the same at every point in there. So that's why this little flux, this is a very tiny flux, and it's really tiny, not because the B is tiny, but because the dA is tiny. Okay, so so the little flux then is going to be equal to B there, but we've already calculated B there is going to be mu naught I over 2 pi r. And the dA is going to be the height. This little area is going to be the height times the width, so it's h dr. Okay, so if that's the case, then, but I don't want the flux through just that little area. I want the flux for the entire thing. So the flux through the entire thing, I'll try putting that here. I'll see if I can fit this in. The total flux is going to be the sum, and I'm going to say start summing at R equals A, and keep on summing till you get to R equals A plus W. Okay, and then it's just going to be equal to mu naught I over 2 pi r. Now I'm not just summing up the flux through one rectangle, but the flux through all of the rectangles. Okay, well, a lot of those things are constant, so I'll pull them out of the integral. Get a little more real estate down here, I think, if I do that. So the total flux through the hoop is going to be equal to, I'll pull out all the constants, mu naught I over 2 pi, and h is also a constant, and I'm left with the integral of dr over r from a to a plus w. Okay, well, that's going to give me the natural log of r. And so it turns out that if I do that, the flux, the total flux, is going to equal mu naught I h over 2 pi times the natural log of a plus w minus the natural log of a. These need to be absolute values. And so, need brackets there too. Okay, I'm going to need to go to another sheet for this, but this can simplify then into just the following. Bring this so you can see it. So this is going to simplify into the flux through that hoop is going to just be mu naught I h over 2 pi times the natural log of a plus w over a. And so there you have it. That's how you do that. And so we made use of the fact that the flux through here was uniform. Or excuse me, the B right here was uniform. So that's what we were making use of, and that's why this right here was the magnetic field, and this right here was the little area h, the height h times the width dr. And so that's how you got that. All right, thanks. Bye.